Is it visible?
Yes, sir. Visible.
So, let us discuss sets and mapping. In your previous learning, you know about what is a set, subset, how intersection takes place, how sets are. You can have union of sets, complements, Venn diagram, and identities and different relations in this set. So far as concerned, and also so concepts like range, domain, into, onto, one-to-one mapping, one-to-many mapping, many-to-one mapping, then composition of mappings, so on and so forth. Then inverse image of mapping, then inverse mapping, like these things. So set is a collection of objects which are distinct and distinguishable. So set is a collection of objects which are distinct and distinguishable. The objects which belongs to a set are called its elements. If an object named X belong to a set capital S, then we can write X belong to capital S, which we read as X belong to S, or X is in S. If we want to express that some object Y does not belong to the set S, we simply write Y does not belong to S. So it is written like this: Y belongs to, में cross डाल दो, S. So Y does not belong to S. It is a general practice to write the elements or description of elements within curly bracket. So sets are the different elements of a set are represented in or written in a curly bracket as shown in the screen. And suppose a collection of numbers or integers 1, 2, 3, and with one of them repeated. So there are four elements or objects, and the collection is a set S. So S can be written as in curly bracket 1, 2, 2, 3. 1, 2, 2, 3. So this is written like this. But it is not a set. The objects of a set can be of any type. For example, sets themselves can be objects and therefore elements of the some other state. If you simply write S is equal to in curly bracket 1, 2, 2, 3, that may not be a set. It is important to understand the conceptual difference between an element and a set. There are many collection of elements, but all the collection of elements are not set. The basic definition of set is it is a collection object provided they are distinct and distinguishable. Let us have an example. It is an important to understand the conceptual difference between element and the state. Let X be an object. Then a set containing a single object X, capital X is equal to in curly bracket small x. It is a set having one element, and the set containing the set capital X is Y is equal to in curly bracket capital X, and capital X can be in curly bracket small x. So this is written like this. So it is shown in the screen. So now Y is another set, and although X belong to capital X and which can be written in curly bracket X small x, but X does not belongs to double curly bracket small x. We give here some notation and useful sets. So R is represented as a set of all real numbers. Z is represented as the set of all integers, positive, negative, and 0. There can be -5, -3, 0, +7, +8, so on and so forth. Z0 is represented as the set of all positive integers not including 0, 1, 2, 3, so on and so forth. C is the set of all complex numbers. Am I audible?
Yes, sir.
Yes, sir.
I think I am disconnected or
No, sir. You were completely
ओके
audible.
ओके ओके तो ये दिख नहीं रहा था, मैं सोचा कि मैं डिस्कनेक्टेड हो गया. ठीक है ठीक है. सो ये दिख नहीं रहा है लेकिन इट इज देयर. ओके ओके ठीक है. So C is the set of all complex numbers. Very often a set is described by a common property, that is its elements there. Let capital R be the set of all real numbers which are positive. Then we can write R subscript plus is equal to in curly bracket X, such that X belongs to R and X is greater than 0. Now use of curly bracket and vertical bar in the notation is shown here. If there are only a finite number of elements, we can write their names within curly brackets separated by commas. For example, as shown in the screen. Okay. It is important to know that when a set is written like this, the order in which the element of set are written does not matter. It is the same set irrespective of order. Suppose you have 5 elements, 1, 2, 3, 4, 5. So you can write it as 5, 2, 4, 3, 1, 3, 2, 1, 4, 5. This can be interchanged. The elements, and the sequence of the elements can be interchanged and it will still be the same set. So your phi is the representation of empty set which has no elements. So here is an example, you can go through it and you can have an idea how open interval, semi-open, semi-closed intervals can be written. In example 16.1, page 9. So then your subset. If all the elements of a set T are also members of another set capital S, then we say that the set T is a subset of capital S and we write it as T is a subset of S or T is contained in S. Okay. When convenient, we can also write it as S contains T. T is contained in S or S contains T. So this is the language which we use. Note that it is always true that a set is its own subset. S is always a subset of S. Also, the empty set is subset of every set. If there is no elements, it is subset of all the sets where there are finite number of elements. So phi is a subset of S. So you can see how these are written. Your Z0 is a subset of Z, is a subset of R, is a subset of C. R subscript plus is a subset of R. There is another symbol used in set theory. S, you see this here in the screen. It is read as X is a subset of Y. Similar to the symbol, X is smaller equal to Y between two real numbers where X could be less than or equal to small y. So this symbol also include the possibility of two sets being the same or equal. When Y contains an element that is not an element of capital X, we say that X is a proper subset of Y. But you always remember that X is smaller than Y, where X is strictly less than Y, and the symbol X subset Y does not always means that there is an element which is not an element of capital X. Therefore, it is safest to treat X subset of Y as an equivalent statement. When a set capital X is proper subset of set capital Y, then that is to be explicitly mentioned. Then you know these things, we will just refresh your idea. recollect those things. Suppose there are two sets A and B, and there are some common elements in A and B. Suppose the A has A 1, 2, 3, 4, 5. B has 4, 5, 6, 7, 8. So 4, 5 are the common elements. So in this case, A and B has an area of intersection, and it is denoted by the intersection is denoted by A. The symbol is like this, B. So A intersection B is also B intersection A. It will not affect whether you write A in the beginning, B in the end, or B in the beginning, A in the end. Suppose 1, 2, 3, 4, 5 intersection 4, 5, 6, 7, 8, 9, and you have 4, 5, 6, 7, 8, 9 intersection 1, 2, 3, 4, 5. So 4, 5 are common elements. In both cases, the region of intersection will include 4 and 5. So if you interchange the two sets, then also there is no changes in the result. It may happen that there is no element in which both in A and B. In that case, the intersection of two sets is an empty set. If there is no common element between A and B, suppose there are two sets. One is 1, 2, 3, another is 7, 8, 9. So there are no common element. So in that case, the intersection will give 5 set. They have no element 5. A intersection B is equal to 5. And A and B are in that case are called disjoint or mutually exclusive. If B is a subset of A, then you can write it as B subset A is equal to B. Given two sets A and B, suppose your B has elements having 1, 2, 3. A has elements 1, 2, 3, 4, 5. In that case, you see all the elements in the B will come in the intersection region 1, 2, 3. So in that case, the intersection of B and A, B intersection A will give you B. Given two sets A and B, the set which contains elements which either belong to A or to B is called the union of two sets. It is denoted by A union B. It is likely joining the two sets without repeating the elements which may be common to both. This process is symmetric. So A union B is also B union A. By using the process of union or intersection, we can keep obtaining two sets. For example, A comma B, A, B and C are three sets. We can form A union B ब्रैकेट के बाद आप लिखेंगे यूनियन सी and it is same as A union B union C. So the order does not matter. Similarly, we have repeated intersections. The process of union and intersection of sets can continue for any number of times evaluated in any order. If A1, A2, so on so forth, An are any sets, then A1 union A2 union so on so forth An, or A1 intersection A2 so on so forth An are written like this. So we can write this in the way shown in the screen. Then we'll discuss Venn diagram. You already know it, but we'll recollect your ideas. Now, to visualize the relations between sets, we show sets as circles, rectangles, or any closed shapes, and place them so that the common or overlapping parts show the sets corresponding to intersections, and the outer boundary shows the union. In the following diagram, the sets A intersection B and A union B are given in thick lines. 16.1 Venn diagram CU. So A intersection B is the thick line shown here. A is rectangle, a bigger rectangle in the left hand lower part. B is in the right hand upper part, and the intersection is the middle part. Similarly, union. Suppose you have A and B, then C. The union will be the bold line covering both A and B. Are you getting it? So, similarly, all the algebraic operations can be represented in Venn diagram. Okay, A intersection B, and this is A union B. So thick line is represented by your shade operation. Then there are certain identities related to sets. Suppose A, B, C are sets. Then A union A is equal to A intersection A is equal to A. Okay. So similarly, other things you can see here. These are the identities associated with set. Then Cartesian product. Before going to Cartesian product, you refresh your idea on ordered pair of two objects, A and B, as the object A comma B. It is called ordered because the position of A and B cannot be interchanged. Give two sets X and Y, we can define a set called the Cartesian product of X and Y and denoted by this symbol X Cartesian product Y as the set whose elements are all ordered paired X comma Y, where X belongs to X and Y belongs to Y, and you can write the Cartesian product as shown in the screen. Here is an example, go through it. Then relations. A relation capital R defined on a set capital X is a subset of the Cartesian product of capital X with itself. This can be written like this. R is a subset of Cartesian product of X. If the ordered pair A comma B belongs to R, we say that A is related to B by capital R, or say A capital R B is true. If A is related to B by capital R, it may or may not be true that B is related to A. An equivalence relation is a relation capital R on a set capital X which satisfies the following three conditions. Condition 1, 2, and 3 are shown in the screen. The first one is called reflexive, second one is symmetric, and third one transitive. Then what is an equivalence classes? Given an equivalence relation defined on a set capital X, we can define subsets of X such that every member of a subset is related to every other member of the same subset and not related to any member of other subsets. So there are some examples. You can go through it. Then next is your mapping. A function or a mapping f from a set capital X into a set Y is a rule by which every element of capital X is assigned a unique element of Y. It is important to note that there is only one element of capital Y which is assigned to a given element of capital X. Of course, there may be more than one element of X which are assigned the same element of a capital Y. Here is an example. Then range and domain of mapping. In a mapping, F X into Y form the set where each element of set X is mapped to some unique element, that is its image f of X belongs to Y. But it is not necessary that every element of the capital Y is the image of some element of capital X. The subset R is a subset of Y consisting of all those elements of capital Y which are the image of some elements of capital X is called the range of the mapping small f. So this can be written like this. We can define a mapping f X into Y. All elements of set X are mapped by F. Sometimes it is more convenient to choose a subset capital D which is a subset of X, and we choose to only map capital D into Y such that F D into Y. In that case, D is called domain of the mapping F. So you can have into mapping, onto mapping, and one-to-one mapping. So F maps X into Y. In the range of mapping, F maps X into Y is equal to the whole set y, we say that the mapping is onto or surjective. So in general, it is possible that more than one element of x get mapped to the same element of y. But if each element small x belong to capital X is mapped to a separate element of y, then we say the mapping is one-to-one or injective. For one-to-one mapping, the statement f of x1 is equal to f of x2 implies that x1 is equal to x2. A mapping or a function which is both one-to-one and onto is called one-to-one correspondence or bijective mapping. The inverse mapping or function can only be defined for a bijective mapping. Here is an example. Then composition of mapping. If x into y and g, y into z be two mapping, then we can define a mapping G of GOF, which takes an element from x to z by first applying f and then g. So GOF x into z, GOF x is equal to GFX. The composition of mapping is the same as the idea of a function of a function. So you can have direct mapping and so also have inverse image of a mapping. For a mapping f x into y and a subset A is a subset of x, the direct image or just image f a is a subset of y which consists of all the elements which are mapped by elements of A. So f of A is equal to fx such that f belongs to A. For a mapping f such that x into y, the inverse image f inverse b of a subset B, which is a subset of y, is the set of all x belong to x such that fx belongs to b. And you can write it as shown in the screen. If the range R of f is not all of y, then for those b which are outside the range of f, that is B intersection R is a phi set, the inverse image is just the empty set phi. So see your inverse mapping.
Sir,
Are you getting it?
sir,
I'm not audible.
सर ऑडिबल सर वो बैच क्या 2024 और 2026 का चल रहा है ना क्या?
मतलब आप मैथमेटिकल फिजिक्स वाले हो ना?
हाँ सर, मैं फिजिक्स का 2024 का एडमिशन बैच में हूँ, लेकिन मैं अभी तक कोई भी
आपका
लिंक
एग्जाम कब है?
नहीं
आपका एग्जाम कब है?
सर मैं तो अभी ही एडमिशन किया है 2024 जनवरी का।
ये उन लोगों का है जिनका 9 तारीख से एग्जाम शुरू हो रहा है, 9th से।
और सर हमारा ग्रुप वो नहीं है, हम कैसे जान पाएंगे हमारा ग्रुप वगैरह?
मैं इग्नू का स्टाफ नहीं हूँ, आप इग्नू से कांटेक्ट कीजिए। मुझे जो लिंक दिया गया मैं उसी से पढ़ा रहा हूँ।
ओके ओके, थैंक यू सर।
I don't know the structural part of these classes.
ठीक है, थैंक यू सर।
ठीक है, सो जिनका 9 से एग्जाम है उन्हीं लोगों का क्लास हम ले रहे हैं।
सर 24 में भी तो ये कोर्स है।
लेकिन 9 से शुरू हो रहा है ना?
हाँ सर।
आपका एग्जाम शेड्यूल 9 से शुरू हो रहा है, 9 से। वो कब खत्म होगा अलग है, लेकिन इट इज बीइंग स्टार्टेड फ्रॉम 8th जून, सॉरी 9th जून। सो मुझे जो बताया गया, मुझे पता नहीं, मैं जो पूछा कब से एग्जाम है, 9th को बोला गया। ठीक है,
हाँ सर।
then your inverse mapping. If the mapping F is one-to-one correspondence, that is one-to-one and onto or bijective, then it is possible to define the inverse mapping because there is exactly one element x belong to capital X. For every element y belongs to y, we can then define for each y which is equal to fx, the inverse mapping F inverse, and it is written as shown in the screen. F inverse y onto x. F inverse y is equal to x. It is clear that both FO, F inverse and F inverse OF are identity mapping of sets y and x respectively. So this is the preliminary idea on sets. Then we'll go to groups. Mathematical quantities like groups appear primarily because of symmetry, which is so essential a concept for laws of physics. So we'll discuss related concepts like group multiplications, tables, subgroups, permutation groups, transposition, even and odd permutation, cosets of a subgroup, cyclic subgroups, homomorphism in next half an hour. So here it is written, we are discussing that groups appear in a in laws of physics, group and similar concept appear in laws of physics because of symmetry. So what is symmetry? Anybody? Anybody have an idea about the word symmetry? Literary meaning of symmetry is what? Then we'll discuss mathematical and physical meaning of symmetry. Anybody?
Is comparable, equal, close to equal, equivalent.
You are not audible. Please put the mic
It
close.
is something like equivalent, close to similar.
Okay. Anybody else? Anybody
The
else?
human body is symmetrical because if you
Anybody?
cut into two
Anybody
pieces,
else? Anybody else? You are somehow right. You are somehow right. You have given an example
thank you,
of
sir.
human body. Human body. So symmetry is something orderly. आप सिमेट्री का मतलब एक अगर बीच में एक रेफरेंस लोगे उसका दोनों ओर सेम दिखेगा. Both side of the reference line will be similar, identical. Okay. So far as human body is concerned, your left hand side is very similar to that of your right hand side. ठीक है. सो सिमेट्री को जब हम मैथमेटिकली समझने के लिए कोशिश करेंगे, हम अगर आप कंसीडर करेंगे कि आपके लेफ्ट राइट के बीच में एक हम मिरर ले लिए, तो लेफ्ट वाला का जो इमेज आएगा वो राइट वाले के साथ आइडेंटिकल रहेगा. अगर इसको बोलते हैं हम क्या, दो टाइप का सिमेट्री होता है. एक हम वर्टिकल रखेंगे वो मिरर को, अगर इधर से उधर तक आएगा वो एक सिमेट्री होगा. अगर होराइजेंटल रखेंगे, ह्यूमन बॉडी को में हम होराइजेंटल रखेंगे, आपका क्या, आपका रखेंगे मिरर कहीं इन बिटवीन योर स्ट्रक्चर, इरेक्टेड स्ट्रक्चर. सो इधर क्या होगा, आपका ऊपर वाला पार्ट जो है नीचे वाले पार्ट के साथ सिमेट्रिक नहीं रहेगा. रहेगा क्या? तो ह्यूमन बॉडी वर्टिकली अगर आप मिरर रखेंगे दैट इज सिमेट्रिकल. होराइजेंटली अगर आप बॉडी रखेंगे दैट इज नॉट सिमेट्रिकल, अनलाइक दैट ऑफ ए स्फीयर. स्फीयर को आप चाहे वर्टिकली रखो या होराइजेंटली रखो, दैट इज सिमेट्रिकल. आप अगर क्यूब, क्यूबॉइड, पैरेललोपिपेड, इसको आप होराइजेंटली रखो या वर्टिकली रखो, दोज आर सिमेट्रिकल. बट ह्यूमन बॉडी आज सिमेट्रिकल इन सम लाइन ऑफ discussion and not symmetrical in some other line of discussion. So mathematically जब हम symmetry को देखेंगे तो mathematically हम देखेंगे कि symmetry क्या है, कि अगर एक मिरर रख लेंगे हम रेफरेंस लाइन में, दोनों साइड अगर आइडेंटिकल दिखेगा दैट इज सिमेट्री. इजीली अगर इसको हम रियलाइज करना चाहेंगे तो ऐसा. तो सिमेट्री समथिंग रिलेटेड विथ ब्यूटी. अगर थिंग्स आर विल बी ऑर्डरली देन इट विल बी ब्यूटीफुल. If things are not orderly, it will not be beautiful. So, in a literary sense, you have symmetry means something orderly, something beautiful. In mathematical sense, symmetry is something which gives an what the participant has told earlier, that something very identical, something very similar things is called symmetry. So, in laws of physics, symmetry is a concept, and your groups are appeared because symmetry is there in laws of physics and in physical behaviors. So now discuss how groups appear. Before that, let us have some examples. A rigid body is symmetric about an axis. then rotation by an angle theta about the axis does not change the state of the body. A further rotation about the same axis by an angle phi also leaves the state unchanged. This shows that the rotation theta plus phi does not change the state. Also, the inverse rotation by minus theta and no rotation, that is rotation by an angle 0, do not change the state. So this group of rotation by all angles is mathematically also a group. Okay, I am discussing this because in a rigid body, if you plane a mirror in between, either are vertical or your horizontal, you see both parts are identical. Then if you rotate it, left part will come to right and right part will come to left. Then also it will not change. If that is not identical, then when you rotate, it will change. The impression or the image will change. Okay, so before rotation, you put just a mirror vertically or a mirror horizontally. You see the upper part side and the lower part side will be identical. The left hand side, the right hand side will be identical of that of the mirror. So mathematically, when we rotate this, the left hand side will come to the right hand side and the right hand side will be in the left hand side and it will not change. So this is mathematical realization of a symmetry concept. So this forms a group. Your rotation by theta, then by phi, and so on and so forth, does not change the state of that body. So rotation or single rotation or double rotation or rotating thrice will form a group by any angle. Okay. Then see example 17.2. Okay. So what is 7.2? Equation of a motion for a free particle in a frame of reference. So you will have the things like this as shown in the screen, and you will finally see that x double dash is equal to x minus v double dash subscript xt, and v double dash subscript x is equal to v subscript x plus v dash x. And similarly for y double dash and z double dash. The velocities define a group of transformations from one frame of reference to another. There is a identity or no change, and inverse, the velocity changes sign, they also form a group. This shows that the equations of motion are unchanged when we replace x to x dash or x double dash etc. using parameter vx or v dash x connecting them. Okay, so this is another example. Let us have a binary operation. Binary operation B on a set X is a rule by which any two elements of a set are assigned a third element of set X of the set. We can say that a binary operation is a mapping from Cartesian product X X into X. We can denote the binary operation by other symbols as shown in the screen. The sum of a plus b of two real or complex numbers is a binary operation on a set of real or complex numbers. The multiplication of two real or complex numbers is a binary operation. Multiplication of two square matrices is a binary operation defined on the set of square matrices of the same size. Okay. So there are associative and commutative relation and like this. So we can define a group like this. A group capital G is a set with a binary operation which satisfies the following three conditions. So what is condition 1, condition 2 and condition 3 are shown in the screen. Condition 1 is the operation is associative. Condition 2 is E belongs to G called identity such that of any G belongs to capital G. And third condition is for every small G belongs to capital G, there exists a unique element G inverse belongs to capital G called the inverse of G, such that G inverse is equal to G inverse or G is equal to E. So this is the definition of the group. Okay. Let us move further. So to realize G is just a set It becomes a group only when a binary operation satisfying the conditions above is defined on it. The same set G becomes a different group with a different binary operation. So strictly speaking, we can say the pair G, 0 or O as the group when there is no confusion what the binary operation is, and we can say group capital G without writing fully this. The binary operation G1 or G2 associated with a group is often called the group multiplication law or group composition law, although it is not like multiplication of real or complex numbers. Also, for convenience of writing, the symbol is here used omitted. Okay, so there are some examples in your page 24, 25. Okay, a group with only finite number of elements is called finite group, and the number of elements of a finite group is called its order. A group which has an infinite number of elements is called an infinite group or a group of infinite order. In the above example, the group on sets of R or R superscript plus are infinite groups. So you see in the screen 17.1. Each row or column of the matrix of product, that is the matrix below the horizontal line and to the right of the vertical line, has all the elements of the group but in a different order. It is so because in a group table, if you have like this, then multiplying on the left by A inverse in both the equation, A is equal to A inverse, C is equal to D, but that cannot happen because B and D belongs to different columns. Then your commutative or abelian groups. In general, in a group multiplication, the order of elements matters. So here come the commutative or abelian group. A group which is not abelian is called non-abelian group. All groups given in the example I am discussing here are abelian groups. It can be proved that all finite groups of order less than equal to 5 are abelian. Then your subgroups. A subgroup is a group within a group with the same binary operation. Let capital G be a group and S a subset. Then S is a subset of capital G. If the set S has the following properties, that is, it is closed under the binary operation of G, that is, if A comma B belongs to S, since the identity must always be in a group, it includes the identity E belongs to S, and if A belongs to S, then A inverse belongs to S. Then S is a group within capital G, and it is called a subgroup of G. Note that according to the definition, the identity by itself and the group capital G are also subgroups. These are called trivial subgroups of capital G. Other subgroups, if they exist, are called proper subgroups. Here is an example. Example 17.4. An orthogonal matrix A is one for which A multiplied by A transpose is equal to 1. This can be also written as determinant of A square is equal to 1. Therefore, these matrices have non-zero determinant and belongs to GL n comma R. The product of two orthogonal matrices is also orthogonal. Then general linear group, orthogonal group, special orthogonal group, these are the things. Then permutation group or symmetry group, SN. Different ways of arranging n distinct objects in a line is called permutation. You know. It is customary to denote these objects by natural numbers 1, 2, so on and so forth, n. There are n factorial ways of arranging these elements. For example, if n is equal to 3, then there are 6 ways as shown below. 3 factorial n is equal to 3. So there will be 3 factorial is equal to 6 ways. What are those 6 ways? 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. As all the arrangements are the same elements in different order, it is very useful to see them as one-to-one correspondence of the set capital X which is 1, 2, 3 into itself. Therefore, every permutation is a 1-to-1 onto mapping x to x. Let us name this mapping in a standard way as shown in the screen. E, P1, P2, P3, P4, P5, so on and so forth. So the mapping is into. Now we can define the product of any these two permutations. And you can see it will be P5 as shown in the screen. This permutation group of 3 objects is called symmetry group S3. A permutation group of n objects is called symmetry group Sn. Then geometrical illustration of S3. Consider an equilateral triangle with a vertices numbered as 1, 2, 3. The first triangle denotes the unchanged position of triangle and corresponds to the identity E. The next P4, where the numbers A, 1, 2, 3, the numbers 1, 2, 3 are replaced by 3, 1, 2, is obtained by A 2 pi by 3 rotation about an axis passing through the center of the triangle and perpendicular to the plane of the triangle. Then further, if we rotate it 2 pi by 3, that is 4 pi by 3 rotation in toto gives P2. Another 2 pi by 3 rotation will bring it back to E, and it is illustrated in figure 17.1. So what about P1, P3 and P5? These are mirror reflections about the line passing through the vertex and perpendicular to the side opposite. Then P3 is obtained with reflection about the line passing through the vertex 3 of E and interchanging 1 and 2. Similarly, P1 is obtained from E by mirroring about a line passing through 1, and P5 is obtained by mirroring about a line passing through 2. This shows that the group S3 is related to symmetries of a regular triangle. This group is also called dihedral group B3. So this I was explaining in the beginning of this chapter, that if we put a mirror vertically or horizontally, you can realize what symmetry is, and it is shown here in 17.5.1 how your P1, P3 and P3, P5 are realized. Then there is an example 17.6, you can go through it. Then transposition and even and odd permutations. Where there is a pair of elements interchange takes place, that is called transposition. The product of such transposition with themselves is equal to identity. A transposition with the identity therefore forms a subgroup of 2 elements. Therefore, there are these obvious subgroups in Sn. So you have even permutation or permutation, so on and so forth to realize it. So see 1, 2, 3, 2, 3, 1, 3, 1, 2. These are even permutation. Your 1, 2, 3, 1, 3, 2, 3, 1, 3, 2, 1, 2, 1, 3. These are all serially and not serially. This will be achieved by even or odd permutation. In some cases, even remains even. In some cases, even becomes odd, so on and so forth. Then coset of a subgroup. Given a subgroup capital H of a group capital G, we can divide the group capital G into many mutually disjoint subsets as follows. We take an element A belongs to capital G which does not belong to capital H. Then we can construct a set A capital H like this as shown in the screen. This subset, which is obtained by multiplying A to every element of capital H on the left, is called left coset of H determined by A. This coset AH contains A is equal to AE because the identity E belongs to H. AH is disjoint from H because if AH1 is equal to AH2 where both H1 and H2 belongs to H, then multiplying by H1 inverse we can get A is equal to H2. H1 inverse belongs to capital H, which is a contradiction because A was chosen to to be not in capital H. Okay, it is important to know that although we have denoted the coset as H because we choose A as the starting point of the construction, all elements in this coset are on same footing, that is, they are equally qualified to represent a coset. So we can keep going till all elements of the group G are covered in some or other coset. So here is an example, 17.7, you can go through it. Then cyclic subgroups. For a finite group capital G, we start with an element A different from the identity. We construct A belongs to G. It is traditional to write as A square and A as AQ, etc. At each stage, each A to the power n is equal to E or to a different group element from E and A, because if A to the power n is equal to A, then multiplying by A inverse we get A to the power n minus 1 is equal to E. If the group is of finite order, that is, if the group has only a finite number of elements, then for some value of integer n, we stop at A to the power n is equal to E. After that, multiplying by A will only repeat the cycle A square, so on and so forth, A to the power n minus 1. This set of elements form a subgroup of G. So elements are A square, so on and so forth, A to the power n minus 1. Because A to the power S, A to the power R, A to the power S is equal to A to the power R plus S, where A to the power R plus S is equal to A to the power M. Okay. Then your cyclic subgroups are permutation group. So the permutations are like this, as shown in the screen. Then homomorphism, one of the important concept. Given two groups G and G dash with binary operation O and O dash, a mapping phi such that G into G dash is called a homomorphism if for any two elements A comma B belongs to G, if phi A is equal to A dash and phi B is equal to B dash, then A dash O dash B dash is equal to phi A O B. We'll omit the symbol for binary operations. It being understood that when two elements of a group are written as a simple product, the binary operation is that of that group. So we can write A dash B dash is equal to phi A, phi B is equal to phi AB for every A comma B belongs to G. It is clear that the identity of capital G must be mapped to the identity of G dash, because phi A is equal to phi EA is equal to phi A. And multiplying this equation by phi A inverse on the right, we get phi E is equal to phi A inverse is equal to E dash, where E dash is the identity of G dash. Also, for any A belongs to G, the homomorphism phi maps A inverse to phi A inverse. So phi A is equal to phi A inverse is equal to phi A inverse is equal to phi E is equal to E dash, where E dash is the identity of G dash. Also, for any A belongs to G, the homomorphism phi maps A inverse to phi A inverse. So phi A is equal to phi A inverse is equal to phi A inverse is equal to phi E is equal to E inverse, which shows that phi A inverse is equal to phi A whole inverse. But apart from E, there can be several elements of capital G which can also map to the same identity element E dash belongs to G dash. Let K is a subset of G is the subset of elements of G which map into the identity of G dash. So several elements of G can map to same identity element. When the group G dash is the same as G, we call such homomorphism as an endomorphism. These elements in K form a subgroup in G because if A comma B belongs to K, then phi A is equal to E dash, phi B is equal to E dash, then phi AB is equal to E dash is equal to E dash, therefore AB belongs to K. Similarly, what is isomorphism? If the identity E belongs to G, the only element which is mapped by a homomorphism phi into the identity E dash of G dash then the mapping phi is 1 to 1, because if A and B are distinct elements of G, then they map to the same element A dash is equal to phi A is equal to phi B, then since phi is homomorphism, phi A B inverse is equal to phi B inverse is equal to A dash inverse is equal to E dash. But as E is the only element mapped to E dash, we must have AB inverse is equal to E or A is equal to B. Thus, a homomorphism for which only the identity maps to identity is 1 to 1. If it also happens to be on 2, that is, the range of mapping is all of G dash, then the homomorphism is called an isomorphism. Two groups which are isomorphic are practically the same in their group algebraic operations. When the isomorphism phi maps the group G into itself, we can have G into G, phi G into G, we call it an automorphism. So here is an example 17.9. Then your conjugation. Two elements A and B of a group capital G are called conjugate of each other if there is a G belongs to capital G such that B is equal to GA G inverse. The relationship is mutual because we can also write A is equal to G inverse B G inverse whole inverse. Actually, this conjugation is an equivalence relation. Any A belongs to G is conjugate to itself. A is equal to EA E inverse. EA E. If A is conjugate to B, then B is conjugate to A as seen above. If A is conjugate to B, G1 A G1 inverse, and B is conjugate to C, G2 B G2 inverse, then A is conjugate to C. So every equivalence relation will make the set as a union of disjoint sets called equivalence classes. An equivalence class is determined by a subset, or every member of subset is related by the equivalence relation. So every fixed element G belongs to capital G defines a conjugation automorphism as phi G, G into G, A G inverse. It is 1 to 1 because GA G inverse is equal to GB G inverse implies A is equal to B, and it is on 2 because for any B belongs to G, there is an A is equal to G inverse BG such that phi G is equal to B. So here is an example. Then invariant subgroups. Pardon. Just as we have conjugate elements of a given group elements, we can think of the conjugate elements of a subset of S of G. Just as we collect all the conjugate elements of a single elements A belongs to capital G to make the equivalence class. So conjugate elements of every element A belongs to S, which is a subset of G. We can write it symbolically as GS G inverse is equal to GA G inverse, where A belongs to S and G belongs to G. This is particularly important if the subset S happens to be a subgroup H. An invariant subgroup or normal subgroup H of a group G is such that all the conjugate elements of H are within H itself. So you can write G H G inverse is equal to H. For an invariant subgroup, the left and right cosets are the same. This is so because for any A outside H, the condition for invariant H means A H1 A inverse belongs to H. Therefore, there is H2 belongs to capital H such that A H1 A inverse is equal to H2 or A H1 is equal to H2 A. The last equality shows AH1 belongs to AH in the left coset in the same element as H2A belongs to HA of the right coset. With this equality of left and right cosets of an invariant subgroup, we can define a composition law for cosets. We choose the left cosets for writing the composition law. AH BH is equal to ABH. The first thing to check is that this definition is independent of the representatives A and B chosen, because we know that if A dash belongs to AH is any other element, then A dash is equally good to represent the coset because AH is equal to A dash H. Similarly, If B dash belongs to BH is any other element, then B dash is equally good to represent the coset because BH is equal to B dash H. Therefore, we must make sure that A dash H, B dash H is equal to A dash B dash H. This is possible because if A dash is equal to AH1 and B dash is equal to BH2 for some elements H1, H2 belongs to H, then a typical element on the right hand side is A dash B dash H is equal to AH1, BH2H is equal to AB, B inverse H1B, H2H. But H3 is equal to B inverse H1B, which belongs to H, because H is an invariant subgroup so that A dash B dash H is equal to AB, H3, H2, H belongs to ABH. In other words, ABH and A dash B dash H are the same coset and the composition of these cosets is well defined. The group of left or right cosets of an invariant subgroup H is called the factor group denoted by G slash H. If G is a finite group of order n, then we know that the order n of the subgroup H, which is also equal to the number of elements in each coset, divides n. Therefore, the order of the factor group of an invariant subgroup is n slash n. So there are some questions, some worked out examples. We can go through it. Are you getting it? Am I audible?
Yes, sir. Yes, sir.
Okay. So let us recollect these things, and after 2 to 3 minutes, we'll start the next course, that is matrix.
Good evening, everyone. Can someone please add me in our WhatsApp physics group? I have sent my number in class message.
आप ये
So
जो
please add.
मैसेज में डाल दीजिए, कोई आपको ऐड कर लेगा.
थैंक यू सर, थैंक यू सर. इन क्लास मैसेज में मेरा नंबर डाला है सर.
हाँ ठीक है, कोई
कोई
ऐड कर
प्लीज
लीजिए
मेरे को
इनको,
add-
जो एडमिन है उनको ऐड कर लीजिए. और ऐड करने के बाद मैसेज बॉक्स में एक मैसेज दे दीजिए, यू आर एडेड.
Sir, can you give some tips how to handle the exams? What kind of questions you can have expect to have?
What is the query?
Yeah, we will be having our first. We are the first batch, so we are little
Okay.
apprehensive of what kind of questions will be there.
You may be the first batch in your RC Bhubaneswar, but there are other regional centers where this course was being run. So please go through the
Sir,
previous year questions of other regional centers.
sir, MSc PH is just being started from last year. So we are the first batch in all India basis.
Okay, okay,
So
okay.
so might be some other course were there, but so far this
Hmm.
PSC MH is concerned, this has been started
Okay,
last year only. So
okay,
many of our, I mean, जो दो साथी है थोड़ा तकलीफ में है, तो anyway,
okay. So, but we
क्योंकि मैंने
cannot do in this regard because there is a well-built structure of IGNU for question setup and moderation. So
okay.
after one and two examinations, it will be clear how the pattern of question paper will be is being set.
And sir, as because there are 5 units, उसको हम
Hmm.
लोग सर हम लोग जब पढ़ेंगे वो उसका अप्रोच कैसे कैसे होना चाहिए, फ्लो फ्लो ऑफ लाइन ऑफ स्टडी, थोड़ा थोड़ा हेल्प
ये
करते तो अच्छा।
ये कैसे बता सकते हैं जब तक आपका एक दो क्वेश्चन पेपर सेटअप नहीं होगा नो बडी कैन प्रेडिक्ट इट। सो हमेशा जो आगे चलता है वो सफर करता है और बाकी लोगों के लिए वो माइलस्टोन बनता है।
हाँ, ये तो सही बात है।
तो यू विल बी सफर्ड but your suffering will give rays of hope, rays of light to other people who will come in the coming years.
सर जो हमारा ये मैथमेटिकल फिजिक्स में 5 ब्लॉक्स है, तो
जी।
वो क्या मैंने उसमें कौन सा ज्यादा ज्यादा एम्फेसिस देना चाहिए कि यार, और
How can
अदरवाइज
I say it unless I have a question paper? How can I say it? It depends upon the person who said the question. Psychology varies from person to person, approach varies from person to person.
यानी
So
हम लोग
you
को
are
एग्जाम।
concerned with your examination. So those people who are having question, who are setting your question and those people who are moderating those question papers, they can better say it. So I can just have your concern on conceptual clarity and other things. And so far as question setup and distribution of things are concerned, distribution of questions and weightage, I cannot help you, I think.
ओके सर, और मैथमेटिक्स फिजिक्स में और क्या कोई क्लास होगा क्या? दिस इज द लास्ट